Okay, today we're talking about random variables. Now, a random variable is a quantitative piece of data, and it's the outcome of a probability experiment. Now, these can either be discrete, where you can count them 1, 2, 3, 4, 5, 6, blah, 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 or they could be continuous. And that would be a range of data that you could have, height or weight or length. So you're in between some values. Now, some important things to remember about probability. First of all, any probability is always between 0 and 1, never negative or anything like that. Now, when we have a true probability distribution and we have every possible value, then if I add up every probability for every possible outcome, it should equal 1. Let's see that in action. So a family has 3 children. If the genders of these children are listed in the order they are born, there are 8 possible outcomes. We're going to assume that all these outcomes are equally likely. So let's list the sample space. Well, I could have a boy, and a boy. Or, well, I could have a girl, and a girl. Well, I could have a boy and 2 girls. Or I guess I could have a girl and 2 boys. I could have 2 boys and a girl, or I could have 2 girls and then a boy. Well, I could also have a boy, a girl, and then a boy, or a girl, a boy, and a girl. That's all 8 possible outcomes. Now, our random variable for this instance is going to be X, which represents the number of children that are girls. So X is the number of girls. And then for the probability distribution, we're going to list out the probability of each of those options. So one option is that I have 0 girls. I could have 1 girl. I could have 2 girls, or I could have 3 girls. So the probability of having 0 girls. Well, there's only one option that did that out of all 8. Having 1 girl. Well, that was here, here, and here. So that's 3 out of 8. Having 2 girls, 1, 2, 3. And having all 3 girls, that only happened once out of 8. Now, to make sure we've covered it all, if I add up all of these probabilities, it should equal 1. So let's add them all up. 1/8 plus 3/8, I'm at 4, plus 3 more 8s, that's 7, plus another 8, that's 8/8. That's a 1. Awesome. So to tell if we have a probability distribution, first we're going to check that everything's between 0 and 1. No negatives, nothing over 1. Cool. Now we're going to check the sum. So if I add those all up, 0.45 plus 0.15 plus 0.3 plus 0.1, it's 1. So this is a probability distribution. Yay. Check the next one. No negatives, nothing bigger than 1. Uh-oh. This one adds up, so the sum of all the probabilities is 1.12. That's too much. So this is not a good probability distribution. Okay, no negatives, nothing bigger than 1. Yay. If I add up all the probabilities, it equals 1. So this is a probability distribution. Now, one of the things I can do with the probability distribution is, well, I can find probabilities, and it makes it easier. So we're going to make a probability distribution for rolling a fair die, meaning it's not loaded or anything. Well, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. The probability of rolling a 1 is 1 out of 6. 1 out of 6. This one, we have the same probability for each option. Using this distribution, I can find the probability of rolling a 2. It's right there. Probability of rolling a 2 or a 4. That's 1/6 plus 1/6. That's 2/6. More than 2. Well, that would be a 3 or a 4 or a 5 or a 6. 3, 4, 5, or 6. That's 4 out of 6. At least 3. Oh, well, at least 3 means we're including 3. So 3 or bigger. Oh, that's the same thing we had in the previous. So 4 out of 6. At most 4. Okay, so that would be 1, 2, 3, or 4. That's also 4 out of 6. Now we can make a histogram from these probability distributions. This one would not be so exciting because they're all 1/6. They'd be all the same height. But this example, we have different probabilities depending on the value of our random variable. So our random variable here is the number of children in a family, and our probabilities are on the y-axis. So the probability of having 0 children is 0.273. So what is the probability that a randomly chosen family has exactly 2? Well, exactly 2 is right here. That would be 0.244. A randomly chosen family has fewer than 2 children. Well, that would be either 0 or 1. So I take the probability of having 0 and add it to the probability of having 1 child, and that is 0.433. What is the probability that a randomly chosen family has either 4 or 5? Again, we're going to add those two together. And that's 0.121. Now, the next thing we're going to do is find the mean of the random variable, and then we're going to find our variance and our standard deviation. So the formula to find the mean of a random variable is pretty easy. We have the sum of x times p of x. So we take each of the random variables times its probability. It's kind of like we're using it as a frequency type thing. Now, our mean is also known as the expected value. And we're using the population symbol for mean because as our sample size grows, we know that these values are going to approach that population mean. So we're assuming that this has been done, this experiment has been done repeatedly, law of large numbers. A true-false quiz with 10 questions was given to a statistics class. The following is the probability distribution for the score of a randomly chosen student. Find the mean and interpret the results. So to find the mean, we're going to take each of the x values times its probability. So 5 times 0.04 plus 6 times 0.16 plus 7 times 0.36 plus 8 times 0.24 plus 9 times 0.12 plus 10 times 0.08. So I would go off to my calculator and add this up. And I get that the mean is 7.48. Now, what does this mean in context, the interpretation? This means that the average score for a randomly selected student is 7.48. You could also think of this as the expected score. This is what I could expect to make. A computer monitor is composed of a very large number of points of light called pixels, and it's not uncommon for a few of these to be defective. X represents the number of defective pixels, and the probability is given here. We want to find the mean. So again, we take each X times its probability. and I really don't need to put this one in there because 0 times anything is just 0. So I've got 0.5 plus 2 times 0.2 plus 3 times 0.1. And so I get my mean is 1.2. And this is the average number of defective pixels. Now, the formula for mean is super easy. The formula for variance is not. You'd have to square each x times the probability, then subtract the mean squared. Oh, that takes forever. Now, to find the standard deviation, remember, variance is the standard deviation squared. These formulas take so long. Let's use the TI. In the TI calculator, we're going to put the random variable x is going into L1 and P of x is going to go into L2. Now, the instructions here from the older calculators, but when we use ours, when we go to one variable stats, because we're only dealing with one variable, it'll have list, which will be L1, and frequency list. We need to include those probabilities. We want it to multiply them together. So we're going to put L2 in for the frequency list. Now, if you are doing this on the NumWorks app, all you'd really have to do is go to statistics and enter your data in and then go to stats, and it's right there. There's a little bit more steps when we do it in the TI. So I'm going to show the TI here. So edit, and I've already entered my data in. So now I'm going to run the one variable stats. And notice I have the list as L1 and my L2 is my frequency list. Even though it's probability, we're considering it a frequency list. And it gives me X bar. That's giving me my mean. Now see, the calculator doesn't know that we're talking about the total population. So it just gives me the sample notation, but we're really talking about the total population. It does give me this symbol, which is my standard deviation. And that's 1.237. Now to find variance from a TI, it doesn't give it to you. The NumWorks, it does. I have to take that standard deviation and square it. So I would take 1.237 and square it. Now in the NumWorks app, it gives it to you. Now we got two more examples that I want to go over. And this is talking about the expected value in terms of figuring out whether we have a gain or a loss. If we have expected value that's positive, we have a gain. If it's negative, we have a loss. So in a game of craps, 2 dice are rolled and people bet on the outcome. For example, you can bet $1 that the dice will total 7. The probability that you win is 1/6. If you win, your profit is $4. That means you won 5, but you bet $1. So you profited $4. If you lose $1. What is the expected value of your profit? So my X here is the profit. So we could either win or lose. If we win, we profit $4. That's a positive profit. And the probability of that is 1 out of 6. If I lose $1. Now the probability of that would be 5/6. 1/6 plus 5/6 is 6/6. To find the expected value, we do the same process as finding the mean, because that's the same thing. We're going to take our X times its probability. So notice that one of the X values, one of our random variables, is negative in these instances. 4 times 1/6 plus -1 times 5/6 gives me -1.167. What this means is we have an expected loss of 17 cents, which doesn't seem like much, but if I played this game 1,000 times, that could add up really quickly. One more. A mineral economist estimated that a particular venture had a probability of 0.4 of a $30 million loss, 0.5 for a $20 million profit, and 0.1 for a $40 million profit. So X is representing my profit, and then we need the probabilities. So I could have a $30 million loss, probability of 0.4, $20 million profit, 0.5, or $40 million profit, 0.1. Let's double check that we have everything. Yes, it adds up to 1. To find my expected value, I'm going to take negative 30 times 0.4 plus 20 times 0.5 plus 40 times 0.1. And we get an expected value of 2. That's positive. That means we have an expected gain of $2 million. That's a venture I wouldn't mind taking.